So we're going to take a look at an example here where we are turning a wedge-dash diagram into a Newman projection. And just so we all draw the same thing, we're going to sight down this bond. So the carbon here on the left that has a closed dot is going to be the front carbon, and the carbon on the right marked with an open circle will be the rear carbon. This is an arbitrary choice, and we could just as easily have looked at it from the other direction. Just as we could also, so let me add that on there. We could look this way. We could actually make this carbon the front one and this one the back one, and look at the rotation around that bond. So any bond, all sigma bonds can rotate. If there's just like a hydrogen at the end, then the hydrogen is spinning. A spinning sphere essentially doesn't give you any conformational difference. It's only when you have more than one atom at the end of the bond. Like if you have the OH and you picture the H sticking out, as you rotate around here, right, that hydrogen can go in a circle. And so you can use the Newman projection to look at any of those rotations, and you can look at it from any direction. So the only reason that we would pick one particular one is so that we can have a common picture. And by the way, if we wanted to look at a model of that compound, we're looking at it from the side. So we see in the plane of the page 1, 2, 3 carbons in a chain, and then the oxygen of the OH, which is the red one. Sticking out at us, we have this methyl group with the wedge down, and this hydrogen on the next carbon, which will be our rear carbon, that's a wedge sort of pointed this direction, up towards the top of the screen. And then this hydrogen back here, as well as this one over here, would be dashed lines. And so we're basically, in drawing in Newman, what we're doing is we're going from a side view to an end-on view. So we're going to take this carbon that's the front circle, the closed circle, or the front carbon, this one that's the open circle, or the rear carbon. We're just going to turn that model so that we're looking down that carbon-carbon bond. Again, we're rotating from what might be a side view to the end-on view of that. We'll call it the C1, C2 bond. And we'll just say that the front one is the C2. We'll make that a closed dot. So the Ch03 is going to be pointed straight up. And again, if we take a look back at the actual model, right, things that are in the plane of the page when we're looking at the side view are going to be either straight up or straight down when we look at the end view. Does that make sense? Okay. And then that means that the OH group is pointed straight down. So on the rear carbon, and I'm going to go ahead and make the rear carbon blue so that it stands out, we have the OH group. And then up to the right, on the rear carbon here, we've got a hydrogen. And up to the left, we have a hydrogen. So we draw that here, H here, H here. We come back to the front carbon, we're going to have two groups pointed down to the right, down to the left. And since we rotated our model from this way so that the left carbon is in front, then that Ch03 group here is going to swing around to the right-hand side. So that means over here, our second Ch03 will be here, our hydrogen will be here. So that's transcribing a wedge-dash picture to a Newman. And if you got a set of these Tinker Toys, it makes it a lot easier. Who wants a set of Tinker Toys now?
Yeah, I'm about to order one.
All right, yes. I don't know how to make that more clear in the beginning. I guess I really should at the beginning of Org 1 just harp on that you really want these. And my apologies for not having been more explicit there, but hopefully those of you that have ordered them, they're on their way. Questions on doing that translation of pictures from the wedge-dash picture to the Newman? Good? Okay. Rotate the front carbon clockwise. And again, it's an arbitrary choice. We could rotate either the front or the back, and we could rotate either direction, but so that we all draw the same picture, let's go clockwise, and we're going to do it in 60 degrees. Now, what that translates to with the model is this front carbon moving like this, right? So we have free rotation around this bond. What the real molecule will typically do is kind of wiggle around in this energy minima where those groups are staggered. Because the more it moves this way, the more this methyl group is eclipsing this hydrogen. And that's basically this bond, which is a cloud of electrons, getting closer to this bond, which is another cloud of electrons, and them repelling one another. And that's called torsional strain. So the minimum of torsional strain is when these groups are staggered or alternate, like we're seeing here, where there's one in the front and then one in the back and one in the front, one in the back, and they're about 60 degrees apart. And again, this conformation would be staggered. The next one, when we rotate 60 degrees, we're going to see an eclipsed conformation. Now, the degree of rotation is also arbitrary, sort of, in the sense that real molecules don't just rotate 60 degrees at once and stop. They just are constantly rotating back and forth a few degrees at a time, and then they make big jumps every once in a while. We're choosing 60 degrees because it's going between these two extremes. Perfect spreading out of the groups on the front and the rear carbon to perfectly overlap. And when we draw that rear carbon, since we're rotating the front one, we're not changing the rear one at all. So we can just go ahead and draw it exactly as it was before, right? And then what we're going to do for the front one, we really should have it exactly on top of that other one. But you can see, like, that's going to be a messy drawing, right? So what we're going to do is stagger it a little bit. And we can either go a little bit past, or we can go a little bit not quite all the way. We can also make that line longer or shorter than the rear one so that we can spread out the hydrogen and the methyl groups so that we can clearly see them both. Now this methyl is this one, right? We also have this methyl group, which is going to be eclipsing, and let me actually draw that line a little longer so that we get past the OH. It's eclipsing that OH group, right? And then our hydrogen here is going to be up here eclipsing this hydrogen. And if we're thinking in terms of rotation, if we just say that this first picture is 0 degrees arbitrarily, then the second one is now at 60 degrees of rotation. And let's do a couple of things here. First, let's see if we can translate this picture, this Newman, back to a wedge dash. And so that we're doing the same thing again, let's draw that front carbon as a dot, or on the left rather, and the rear carbon, or the open circle carbon, the blue one, on the right-hand side. That way we're all adopting the same transformation. which is going to basically be taking this picture. So this is our first one, 0 degrees. Here we've rotated 60 degrees. So now we have a methyl eclipsing a hydrogen, a methyl here at the bottom eclipsing our red oxygen, and the two hydrogens in the upper left eclipsing each other. And we're going to take that and lay it sideways back to where we started. So this is what we're trying to draw. And this hydrogen, right, this hydrogen actually also has rotational freedom around that oxygen-carbon sigma bond. So we could draw that wherever, but we're not as interested in that right now. What we're really focused on is the rotation around this C1, C2 bond. So what we'll do here is take a look at our model, and we'll actually go ahead and draw on a piece of paper next to it. And so what was the front carbon is our closed circle carbon is going to be this one right here. It has the two methyl groups. Now we can see that carbon-carbon bond. Here's the rear carbon, the one that we were looking down. All right, so Newman, wedge-dash. What elements are sticking out towards us? This methyl group and this hydrogen. And I can put my hand in between, right? You can more clearly see what's sticking out and what's flat. Those two groups are going to have wedges. And notice that, and we'll contrast it to the other one in the middle. But then on each of those carbons, there's a hydrogen that's dashed. And it doesn't matter. I arbitrarily chose to put the two hydrogens sort of inside the wedges, if you will. You could put the hydrogen here or the hydrogen in the back here. It doesn't matter as long as the wedge and dash are next to each other. Okay? And what we're doing is, what we're saying is we're actually drawing this, right, where the hydrogen, front hydrogen is directly in front of the rear hydrogen. And what we're drawing is either this or this, so that we're not trying to draw one on top of the other. And then in the plane of the page, so no wedge or dash, we're going to have the CH3 on the front carbon and the OH on the back carbon. So let's redraw that picture over here. So again, we had on the front carbon, CH3 in the plane of the page, CH3 wedge up here, dashed hydrogen, and then on the rear carbon, OH, hydrogen wedge, hydrogen dash. And notice that you can see that the elements that are eclipsing one another are going to be the ones that are lined up. Right, so the CH3 on the front carbon and the OH on the rear carbon that are both in the plane of the page and pointed down, they're lined up where they're eclipsing each other. Right, and then the CH3 that's sticking out at us and the hydrogen that's sticking out at us, they're eclipsing each other too. So in a wedge dash picture, when you have two wedges that are both up, for example, you know you've got an eclipsing conformation, at least if you've got a open chain like this rather than a ring. Note in contrast, the things that were above the bond that we're looking down on our original picture, on the right or left hand side, you've got a CH3 that's in the plane of the page. And then on the right hand side, you've got a hydrogen that's pointed back and a hydrogen that's pointed in the front. And so neither of those is eclipsing the CH3s, but they're both offset a little bit. So we're going to think of this in terms of an energy diagram, and we're going to look at the y-axis as an energy diagram is always energy. And the x-axis in this case is going to be degrees of rotation. And so what we need to do is analyze the sources of strain in our molecules. And we want to remember one key thing with these energy diagrams is that in terms of the energy levels, eclipsed is always going to be greater in energy or less stable than staggered. So every eclipsed picture should be higher in energy than the staggered pictures. And if we wanted to, we could draw the x-axis along here just so we have our pictures at the bottom. I'm going to flip back to the previous slide so we can look at the Newman projection a little bit bigger. And what we're looking for is sources of torsional strain caused by large groups being gauche to each other. So this is creating torsional strain. And there's only one situation here where we've got that happening, right? So that's not bad. If we take a look at the other staggered conformations, right, so 0 degrees is staggered, 120 is staggered, 240 is staggered, and of course 360 will be staggered because that's the same as 0. Are there any structures there that have fewer methyl alcohol gauche interactions? In other words, can we get away from having the OH being gauche to a methyl group? If we look at our staggered conformations, right, 120, the OH is actually gauche to 2 methyls. 240, it's gauche to a methyl. And so it's always, because there's 2 methyls, you just can't get both of them anti to each other. Worth pointing out, by the way, if we go back to our picture here, better than gauche is to have those 2 groups 180 degrees apart. So this Ch03 and the OH, these are what we say are anti to each other. They're 180 degrees apart. They're not bumping into each other at all. And I point that out just so we're familiar with the terms. Now, going back and analyzing the energy levels, we've got at 0 degrees and at 240 degrees, we each have a methyl hydroxy or a methyl alcohol gauche interaction, but that's going to be the least unstable. So if we want to think about the relative energies of those two, they're at the same energy. Right? And if we want to make that clear, we can draw a dotted line across. We're not worried about the numbers on the y-axis. You can actually calculate that with ChemDraw, but we're not going to bother. The structure at 120 degrees, though, because it has 2 places where a hydroxy, the OH rather, and the methyl group are bumping into each other, that's going to be a little less stable, a little higher in energy, right? So we want to keep in mind high energy is unstable or less stable. Lower energy, more stable. So all our staggereds are going to be about this, or going to be in the lower, let's say, 1/3 of the graph. So we'll look at the eclipsed conformations. And if we'll hop back to this one here, we've sort of got 3 levels of eclipsed, right? It's never good to have things eclipsing, but 2 little groups eclipsing one another, that's not really bad, right? That's okay. A little group and a big group eclipsing each other is going to be more unstable. But the greatest source of strain is going to be 2 bigger groups eclipsing each other. So that's going to be the worst situation. And if we go back to our energy diagram where we've got all the structures, we're just going to look for the places where the Ch03 is eclipsing the OH, right? And so we have that happening here. We have the other methyl group eclipsing the OH at 180, and then at 360, there are only these less in the orange and green, or sorry, orange and red look about the same, so I'm going to use yellow. You've only got big little interactions here, so that's not as bad. There's no big thing eclipsing another big thing at 300. So 300 is going to be less unstable than 120 and 240. Sorry, 60 and 180. These are, I'll highlight all the eclipsed ones. That and that is the same, and that's the highest energy. They're least stable. So I'm going to draw that as high up as I can without making lines across anything else that I've already drawn. And then the one at 300, where we don't have any big thing eclipsing another big thing, is going to be a little less unstable, but it's still going to be in the top third of the graph. And then if we want to complete the picture, all we need to do is to draw a line that's connecting a nice flowing curve that goes from 0 to 60 to 120. Oops, I put 180 right above 240, my bad. To 180, to 240, to 300, and we could even come back if we wanted to come full circle back to 360. So that would be our energy diagram.